Hey, and welcome to The Explainer. We humans get language. It just kind of clicks. But how in the world do you teach a machine, something that only thinks in ones and zeros, to actually grasp the meaning of a sentence? Well, let's dive in and see how it's done.
Right. So you and I can look at this and we get it instantly. But for a computer, this is just a sequence of letters and spaces. It has no intuition. It needs a method, a process, to figure out how these words are all connected to create one single coherent thought. And here's the secret. It's not just about knowing what book or flight means. The real magic is in the syntax, that invisible grammatical scaffolding that holds the whole sentence together and gives it its shape, its structure, and ultimately its meaning. And that whole process, it has a name, of course. It's called syntactic parsing. The best way to think about it is like creating a blueprint for a sentence. A parser takes this flat line of text and reveals its deep, hidden structure. And that is the absolute first step towards any kind of real understanding. So what does this hidden structure even look like? Well, it all kicks off with a pretty simple idea. Words don't fly solo. They actually team up. And these little teams are called constituents. So take a phrase like the morning flight. Those three words, they act as one single piece, a noun phrase. You can swap it out, you can move it around the sentence as a block, because grammatically, it's a single unit.
Okay, so how do we actually model this? The first big idea, the first approach, is to think of a sentence as being built from these constituent blocks, almost like Legos, all stacked together based on a specific set of rules.
And that set of rules is called a context-free grammar, or a CFG for short. It's basically a recipe book. It's full of these little rules called productions that tell the computer things like, hey, a sentence can be made of a noun phrase followed by a verb phrase. It's a formal recipe for building a sentence. So let's look at a really simple grammar here. See these rules? They're the building blocks. That top one says a sentence, S, is made up of a noun phrase, NP, followed by a verb phrase, VP. Then the next rules break those down even more. So to build the flight, a parser would use that NP rule. See that a det can become the, and a nominal can become flight. Every single sentence is just a bigger, more complex combination of these simple rules. But, that's not the only way to look at this. Instead of focusing on these big blocks or phrases, what if we just zoomed in on the direct connections, the relationships between individual words? This shows the two viewpoints perfectly. On one side, you have that constituency view with all the nested boxes and building blocks. But on the other side, you have the dependency view, which looks way more like a web or a family tree. It's not about groups. It's all about direct one-to-one links. This word depends on that word, period. And that is the absolute core of dependency grammar. Every single arrow you see connects a head word, the boss, to a word that depends on it, called the dependent. What's so cool about this is that this structure directly shows you who did what to whom. And these relationships get these really specific labels that tell us exactly what each word is doing. For instance, NSUBJ flags united as the subject of the verb canceled. DOBJ marks the flight as the direct object. It creates this super clear, direct map of the sentence's meaning. Okay, so we've got these two really powerful theories of how grammar works. But how does a computer actually use them to build one of these trees? How does a parser, think? Well, for that building block approach, a classic method is called the CKY algorithm. Just picture a big grid right underneath the sentence. The algorithm starts with the single words at the bottom and then just methodically tries to combine them, checking its rule book every single step of the way. If a combination is valid, it adds it to the chart, building bigger and bigger blocks until, bam, it finds a valid structure for the whole sentence. Dependency parsing, on the other hand, can feel a bit more like a dance. A common type, a transition-based parser, just reads a sentence one word at a time, making a series of very simple choices. It can shift a word into its workspace, or it can create a left or right arc to connect two words together. That's it. Let's watch it in action. The parser has this little workspace called a stack. In step 0, it just shifts book onto the stack. Easy enough. Step 1, it shifts me. Okay? Now it has 2 words to play with, so it can make a connection. In step 2, it does a right arc, which basically says me is a dependent of book. It just keeps doing the simple shift and link dance until every single word is connected into that final tree. Now, all of this sounds pretty neat and tidy, right? But there is a massive problem hiding in almost every sentence we say or write. And that problem is ambiguity.
And nobody, and I mean nobody, captured this better than Groucho Marx. One morning, I shot an elephant in my pajamas. How we got into my pajamas? I don't know. It's hilarious, and it perfectly illustrates the problem. See, what's happening there is called attachment ambiguity. In that quote, the phrase "in my pajamas" could attach to 2 different places. Does it attach to the elephant, meaning the poor elephant was wearing the pajamas? Or does it attach to "I shot," meaning Groucho was in his pajamas when he did the shooting? Grammatically, both are totally valid structures. So that's the million-dollar question, isn't it? If a sentence can have multiple valid blueprints, how on earth does a parser pick the right one? How does it know which meaning we actually intended? The answer, in the modern world, is data. A lot of data. Parsers today learn from these huge resources called tree banks. These are massive collections of sentences that actual human linguists have painstakingly gone through and tagged with the correct parse tree. They're basically the ultimate answer key. And when I say massive, I mean it. To create just one of these resources, the CCG Bank, experts had to sit down and annotate, check, and translate the structures for almost 50,000 sentences. By crunching through all of these correct answers, a parser starts to learn the statistical patterns of a language, so it can make a really good guess when it hits an ambiguous sentence. And believe me, this isn't just some abstract computer science problem. Syntactic parsing is the engine running under the hood of so much of the tech we use every single day. It's how Siri and Alexa figure out what you're asking, how a search engine can understand a really complex question, or even how your grammar checker knows that a sentence just feels wrong. So, we've come this far. We've actually taught machines how to draw a grammatical blueprint for our language. They can map the words, they can identify the structures, but mapping a sentence, is that the same thing as truly understanding it? And that leaves us with a pretty deep and fascinating question. What's the next step on this journey to real comprehension?